it is my pleasure to introduce Alexander Kurz from Chapman University, and he will talk to us about dualities from double categories of relations.
Okay, so I will spend most of the talk in explaining, setting up the scene for what I describe in the abstract. So mostly background. So first about duality. So this is duality in the sense of stone duality. And I will assume that we've seen like Boolean algebras and stone spaces, or the generalization to distributive lattices and Priestley spaces. So that's our starting point. And then the question is, like in this duality, we have, for example, Boolean algebras with Boolean algebra homomorphisms on one side. And so now the question is, what happens if you replace the homomorphisms by relations? So from functions to relations, what's the duality for relations? Okay, so actually, this goes back to work I've done with Drew Mosher and Achim Jung. So that the main part of that work was exactly what I said before, replacing functions by relations in the duality. So in this talk, I will focus on an application of this where the relations are part of the structure of the objects, right? So objects with relational structure. And in order to bring these two perspectives together, relations as arrows and relations as part of the structure in the objects, I will use a double category theory view on relations. So I think I will spend some time on this because I think it's really super useful. It's not the way we started out, but I now think that's kind of the right way to think about relations. And so I want to explain a little bit about this. And I took this from papers by Granis and Perret, and more recently by Mike Schulman. Okay, so before we go to the double categories, what is a relation in our setting? So the relation is two things. It's a subobject. So maybe I should write it more like in this way, like a span, right? So that's a common view of saying what a relation is. A relation is an object in a category with two projections. That's a relation from A to B. But also we are working in an order-enriched setting, which means that there's an additional property. And so another view of relations is like as a two-way functions from A times B, right? So we map to 1 if the pair is in the relation, and to 0 if the pair is not in the relation. And the reason why the second view is also of importance to us is that we want this function to be monotone. So we have two conditions, kind of this span or subobject condition and a monotonicity condition. And okay, so kind of the most important example for this talk is what happens in distributive lattices if we do this. So we need to see what the two conditions are. The span condition or the subobject condition essentially tells us something like that such a relation looks a bit like a sequenced calculus turnstile. So we have the right behavior with respect to conjunctions and disjunctions. And then also we have the monotonicity gives us the familiar weakening condition we also would expect from a sequent. Yeah?
Sorry, would you mind clarifying how the monotonicity condition interacts with the relation? Or are we just asking?
I mean, this was like on the previous slide, the definition, we just put these two conditions next to each other. And if you make, if your question is like how combinatorially this interacts, it can get quite intricate actually.
Okay.
So I don't know whether that was the direction of your question.
Okay. Yeah, no worries. Thank you.
Yeah.
I have a question. Where does distributivity appear here, or this can be stated just for lattices as well?
This can be stated for lattices as well. So essentially this works in any category, but you need some conditions to make it work nicely. But really what you require is that the legs of the span are homomorphisms in the category. Okay, so now we come to, I want to say a few words about the double category point of view. So the idea is we started with a category, could be distributive lattices, could be Priestley spaces, could be some other category we're interested in, and then we want to look at relations in the category. So now we know what the relations in a category are. So they are these spans which also satisfy the weakening condition. Now the question is, how do we organize everything together? And it turns out that the best way of doing this is to keep both the functions or the morphisms and the relations in the same structure. So we need more than a category to do that, right? And so the traditional, or a good way of doing it is to organize this in a double category. So we all know that a category has objects and arrows. So in the line here, you see, this is kind of intended to be the object, and this is intended to be the arrows, right? And but now the objects are a category, and the arrows are also a category. So we don't have a set of objects and a set of arrows. We have a category. We have a category of objects and a category of arrows. And the relations will be the objects in the category of arrows. And then the question is, what are the arrows? The arrows in the category of arrows, and they are these squares. So basically, the way we draw this is we draw relations as horizontal arrows. And then an arrow between relations is a square where the vertical arrows in the picture are functions. So we have relations and functions in the same kind of structure. And yeah, so the definition of such a square, which is an arrow in the category of arrows, is like what is indicated in the picture. So you have two relations, you have two functions, and then you declare this to be an arrow or square if the subset relation holds. And that's the usual subset relation which we have with relations. So we have a lot of structure here, and I want to explain why this structure is important to us. So if I write rel C here, I mean just relations as arrows, no functions, no at all. So of course one can do this, and these categories are important. But one thing that we lose there is a good notion of limits and co-limits, right? And so that's an obstacle we overcome if we put the functions back into the picture. Then I said that we want to do duality for relations. So this took us actually quite some time to work out with Drew. What gets turned around and what doesn't get turned around. So here in this double category theoretic view, it's really natural to say the dual of a double category, a double category can have many duals, right? You can turn around many different things. But what we need is really this one. So that's kind of a nice way to remember that what turns around is not the relation. So we do duality for relations, but the relations don't turn around in the duality because they are objects in C1, right? And what turns around is the arrows in C1, which is the order between the relation turns around. So the the functions turn around and the order between the relation turns around under duality, but not the relations. And then the reason why we actually had to introduce the double categories was a technical one. When you want to extend adjunctions, say between posets and distributive lattices, to relations, this doesn't work if you have relations as arrows, because then the unit and the co-unit need to be relations, and that just doesn't work. If you do this kind of double category theoretic view, the unit and the co-unit will be functions again. So this just kind of turns out to be the native notion of a junction in the two category of double categories, just does the right thing. So that was the technical reason we came up with this. Or we needed this.
Can I ask you?
Yeah.
It's good to understand. Should I think of this as a generalization of the relation algebra of relations? Because in the case where, because we just include, it's just inclusion of relations, but now we're keeping track of the domains and the ranges and
And the functions, everything, yeah.
It's if I forget about all of that, it's just the ordering of
Yeah.
relations.
Mhm.
Thank you.
Of weakening relations.
Of weakening relations.
Weakening relations, yeah. Okay, so I will say later why we actually need to work with weakening relations, even if we're just interested in sets and Boolean algebras. We still need to use weakening relations. I will come to that. Okay, so actually, if you look at this double category, now we have a category of arrows and a category of objects. So we get this kind of picture, and in the paper with Drew and Achim, basically, we were mostly interested in relations as arrows. So which means like you cut out this part, right? But here we do something else. So we also start from here. But what we're doing now is we are restricting to the objects. So we're restricting to the sub-double category where the object and relations here are endo relations. So now this is the way to get to relational structures as objects. So this kind of for us, this is nice, these double categories for this talk, because we have these kind of two different perspectives in one picture. And we will see that this helps us to get a large number of corollaries about different dualities in a uniform way. Okay, so let's see. Yeah, so we still need to say how we actually dualize relations. I didn't say this yet. So the general theorem in the paper with Drew is we take an adjunction between two order-enriched categories, A and B, and then we ask whether we can extend this adjunction to these double categories of relations. So we have a list of sufficient conditions, and then we have a list of examples that are special instances of this general theorem. So in this talk, I only need one special instance of this general theorem, which is the one which specializes to the adjunction between Priestley spaces and distributive lattices. And so I only need to tell you what the duality is doing in this special case. And so the functor I'm considering here is like the homing into two, right? So that's the usual functor that leads us from Priestley spaces to distributive lattices and vice versa. Actually, I wrote here posets, but that really doesn't matter for the explanation of how this duality works. Okay, so what do? We take a span, right? A relation is a span, and then we know how duality works on functions, right? So we apply the ordinary Priestley duality to the legs of the span. This gives us a cospan, right? And then we turn the cospan back into a span. This is a kind of limit, which is, it's a kind of pullback, but it's an ordered version of a pullback. So if we turn the cospan into a span by collecting all pairs such that the left-hand side is smaller than the right-hand side, instead of equal, right? So it's an ordered version of a pullback. And this is why we need to work with weakening relations, even if we are only interested in the discrete case, right? So this, that you can both tabulate and co-tabulate a relation, that spans are the same as cospans as far as it comes to relations. That doesn't work in sets, right? In sets, a cospan would kind of identify too much. You can't co-tabulate all relations in set. But you can co-tabulate all weakening relations in posets. So we take an ordinary relation in sets, we dualize, we get the cospan. This cospan is a cospan in ordered sets, and therefore it can we consider it the cospan. Yeah, and you see why it's in ordered sets, right? Because we go to subsets, and so we can always say that one subset is smaller, or that one set is a subset of another subset. So concretely, if you work this through, you get this kind of condition which you may have seen many times, right? So this is actually something that comes up in all kinds of contexts. You are interested in a relation between subsets A and B, and the relation between the subsets is that A is related to B if the direct image of A and the relation R is contained in B, right? So we start with the relation R, and then we get a relation, a dual relation on subsets. What's the definition of this dual relation on subsets? It's that it relates A and B if the direct image of A under the relation is contained in B. That's what I mean. It's a huge apparatus. You're kind of using here to come up with, and in the end you get out this simple definition, right? So which is very familiar to many of us. But yeah, so I think it's interesting because, like, if you see this in that there may be some duality of relations in the background. Okay, so now we just use this kind of, we put all the parts together, and then we get this corollary here, which says that if I have a Priestley space X together with a relation, and this relation is a Priestley relation, and it satisfies this weakening condition, then the category of these relational structures is dually equivalent to distributive lattices equipped with a DL relation, and they are known as subordinations in the literature. So I wasn't aware of this terminology until recently, and yeah, so we can rephrase in this terminology. We can just rephrase this corollary by saying the category of Priestley spaces with close weakening relations is dually equivalent to subordination algebras. And let me see how am I doing in time. This is basically, I think I still have 5 minutes.
Yes.
Okay, so then if I go to the actual abstract here, so we covered basically all of this, and the corollary I just had on the slide is this one here. So for the last 5 minutes, maybe I just want to tell you that we can use this machinery to now get kind of in a uniform way a whole range of similar corollaries. So how does that work? So first of all, this is Priestley spaces and distributive lattices. When I looked at the literature, I found that most theorems are interested in stone spaces and Boolean algebras. But the thing here is that the definition of a subordination, even for a Boolean algebra, is a distributive lattice relation. So a subordination, even if you're interested in Boolean algebras, the relation doesn't involve negation. So we are working in the BA-based subcategory of DL-based relations. So this is why this terminology is sometimes a little bit kind of clumsy, because but it's how this order enriched stuff really works, right? So you have to work in order enriched, and then if you want to do duality for relations only for sets, you need to restrict to the discrete part of the order enriched duality. The duality is always order enriched. So yeah, so the second corollary is just the Boolean algebra based version kind of restriction. Then we can exploit that we have this that the relations are ordered, right? So for example, we can say that a relation is reflexive by saying that it contains the identity smaller equal R, right? So this is information we have in the category, so we can dualize it. And this is, if you dualize it, because the order turns around, you get this, you get this below identity. That's, so if you have a reflexive relation, means ID is smaller or equal to R. If you turn this around, it's a, you get this below identity constraint. And then you can do something similar for transitivity, right? R composed with R is contained in R. That's again something that we can express in the category. And then if you turn this around, you get the condition which is often called interpolative. Don't know. So it's just again dualizing transitivity. And yeah, the third one is a combination of the two. And then there's another thing you can do that you can say, okay, I'm interested in modal logic. What is a cryptic frame? A cryptic frame is a relational structure. So, and okay, so let's do this topologically. So we have a stone space with a relation, and they are known as descriptive general frames. So now we can dualize this relation using our kind of duality of relations, and we get a subordination. And this is from a paper by the Bizanishvilis and Surab and Ilfenema. So they make this like observation that one can really characterize on the dual side quite easily what this condition to be a descriptive general frame means for the subordinations. And it is that these downsets, okay, so maybe I should, so maybe it's not important to look at how the definition, how the condition really works, but the point here is really just to say that we can kind of easily mirror this on the algebraic side, this condition of a descriptive general frame, and then again we get this this theorem falls out from our general approach, and then also the conditions we have seen before involving the order of the relations kind of can be combined with this condition, and so we get another set of corollaries kind of in a modular and uniform way. Okay, so that's I think what I wanted to say. Really, what I've done is just put together the work with Drew and Achim, and then I reviewed the literature on subordination algebra, so I'm not claiming any new results here, just wanted to show you that we get all these results from the literature in a uniform way using our approach. And conclusion, so if you work with relations, double categories of relations, are really nice for the reasons I explained. Then this condition, direct image of R contained in B, if you see this, then maybe there's stone duality for relations lurking in the background. And and sometimes we can get dualities for relational structures by applying the duality to the relations as objects. Okay, thank you.
We have time for some questions. Yes.
Yeah, so this R of A being a subset of B, do you have any examples that you didn't talk about in your talk where it arose in the wild and you, now that you know this, recognize it as being stone duality somewhere else?
So it arose in the wild, like in domain theory. So in domain theory, there's a long history of these kind of structures, and this is also where we started. So we wanted to kind of unify a lot of these results. So I don't know whether that answers your question, but there's a whole history of these relations and dualities for relations in that field.
Yeah, truly.
Mm-hmm.
So how about the non-distributive case? Can you use any of this to get dualities for non-distributive lattices?
We looked a little bit at some semi-lattices, but we didn't really look at lattices as far as I remember, right? So,
Yeah.
But that would be definitely interesting to look at.
I think relations aren't very nicely behaved on general lattices. I think that's kind of an issue.
I've got a bit lost to all these corollaries. So what's the main theorem again?
So the main theorem is just that the dual occurrence between distributive lattices and Priestley spaces extends to the double categories, which also have the relations.
So what is the, okay, so then that's some kind of a dual double equivalence of double categories? Is that?
So this is, yeah, so you have, I mean, these double categories form two categories again. So you have everything, like you have a notion of adjoints in between these double categories, etc. Yeah, I mean, it takes some time to kind of unwind the definitions, but conceptually it's very clean.
And also that main theorem is not specific to DL and Priestley. It's sufficient conditions for any kind of standard adjunction to lift to the relations.
Right, okay, wow, okay.
So semi-lattices and topological semi-lattices, right? That duality also works. Or posets and completely distributed lattices. Topological distributed lattices. It works there as well. So we have at least a small family of examples and a fairly general theorem. And
yes,
unfortunately, not so many other examples.
But it's amazing that you get so many corollaries just by sort of switching the point of view, right? Instead of looking from left to right, you look from top to bottom.
Yeah. That's what getting the category theoretic
Yes.
picture right
Yeah.
buys you.
So.
Other questions or comments? Let's thank the speaker again.
Thank you.